Hello, welcome. I'm very glad to be here. This is actually a new style meeting for me. I've never been to something like this before, but I'm really enjoying it. I like new experiences, and maybe by way of introduction, I've had a number of fun experiences along the way. I've been a chief maintainer for a free software foundation project. I've been a postdoc. I've worked in a startup company, and now I'm a professor at a university where I do research in machine learning. And today I get to talk about two things that I love a lot: machine learning, which I've loved for many, many years, and Scala, which I've loved for just a few years. What is machine learning? It's essentially the study of computer programs that automatically improve their behavior with experience or training data. One way to see this is they're machines that program themselves, but don't worry, this is not going to put programmers out of business, because it's actually going to make your life harder in some ways. Because what this really means is that it's about writing a program that encapsulates within itself enough structure to represent an immense number of different possible solutions, and it's then we use data to then estimate the parameters that guide the behavior through this structure of different possible solutions. And interest in machine learning has been exploding in the last decade or more, because so many of the things that matter in the world that we care about are really driven by machine learning. Like genomics, which is essentially all about finding patterns in gene data. It's really revolutionizing biology. We have free web search and a lot of services from Google because they're machine learning algorithms that have been very highly tuned within Google to show us relevant ads that people actually click on. There exist already self-driving cars, and maybe we'll all have one sometime soon. And at the heart of this, in order to handle the uncertainty in the world, machine learning algorithms help make this possible. And machine learning is a big part of what makes Siri work inside of our iPhones. And how do I know that, actually? Well, before Siri was an Apple product, it was a startup company. And before it was a startup company, it was a federally funded research project with a lot of academics involved, including me, actually. So I want to talk a bit about machine learning in a bit more detail. Sure, great, yeah, if this helps. And particularly about its structure. So let's start with a very simple example like spam filtering, in which you observe some email messages. And we're going to call these are the observed random variables. And I don't mean variable in the programming sense. This is like in the statistical sense. And it's the job here to then, for each one of these, predict whether it's spam or not spam. For each of its corresponding things. And the way, this is the predicted random variable. And the way that this is often set up is with a function that I'm drawing here, which takes as input the values of the two here random variables that it's observing, and produces as output a real valued score that you can think of as a compatibility score for how compatible do I find the values in these variables. So like if I see Nigerian bank account here and I see spam, then I think, well, that sounds pretty compatible. And for not spam, I would say that's less compatible. And it's the job then of, so these functions are called factors. And it's the job of probabilistic inference to cycle through all possible values in the predicted random variables to say which ones score best in order to pick what we think is the best answer. And what I'm drawing here is called a factor graph. It's a particular kind of Bayesian network or graphical model that it's really becoming the lingua franca for so much of probabilistic modeling that's at the heart of machine learning. So let's take a little bit more complicated example, like Chinese word segmentation. So in Chinese, sometimes one character is a word, but sometimes a word is actually 2, 3, or 4 characters. But when the Chinese write things, there are no spaces between words. It's just, when a Chinese person reads this, they just are finding the spaces themselves in their head as they read it. And so to do natural language processing, which is actually my particular area of research, it would be very nice to find these word segmentation boundaries to do later kinds of processing. So we observe random variables that are the Chinese characters, and we'd like to determine which ones are the start of a word and which ones are not the start of a word. And we can do these with some factors here. But this is a task in which, when I'm determining that this is not the start of a word, it would be very helpful to know whether I thought that the previous word was a start or not. It's like the context of my solution so far. So we want to add factors that capture this as well, sort of compatibility of our neighboring decisions. And this makes inference a bit harder, right? Because I can't independently decide for each of these red or green variables which value to give it, because they all interact with each other. And so naively speaking, I need to consider all possible labelings of this sequence, which is the size of that set is exponential in the length of the sequence. But thankfully, for graphs that are tree-shaped, there are efficient dynamic programming solutions that can make this fast. OK, and this kind of model is actually called a linear chain conditional random field. It's one of the most widely used methods for sequence modeling in natural language processing. Okay, so then there are other kinds of tasks that lead to really hairy structures, like the following: information integration. So say that you're trying to do a study of medical outcomes, and you'd like to gather data from 100 different hospitals spread across the country, and so you want their database of patients, and you want to integrate those together so that you can do some data mining on the results. But each hospital's database was built by a different DBA with a different schema, different ways of setting up the values, and you would like to unify these all together into a single database. So this involves doing schema matching, essentially aligning the columns of the database against each other. Co-reference, essentially aligning the rows against each other, because the same person might have been a patient at more than one hospital. And then finally doing some canonicalization to decide, well, how should I represent the canonical values of this merged database? And it's a quite complicated task. I'm not going to get into great detail about the structure of these models, but I can say just a few things. In these models, we can do better if we, so each of these are representing a record from the original database. This is saying, I think that these all go together. These are rows. And we actually have factors on partitions of this model. So we have, in a way, as many factors as there are partitionings, possible partitionings in the world of this data, which is, it's called the Bell number. There's a super exponential number of partitionings. I can't possibly create all these factors ahead of time. I have to be creating them on the fly as I'm sort of considering various hypotheses. And then there are extra factors from the model as well. And this is just for the row alignment part of it. Schema alignment looks a little bit like that as well, but it's more complicated because there could be hierarchical relationships in how the schema is organized. And furthermore, I want to actually be doing both of these tasks at the same time jointly because they interact with each other. And it's just incredibly hairy. And so how to do this is a big issue. And it brings up big issues for me as a machine learning researcher, because just how to do inference and parameter estimation in this model is very tough. But today I want to talk about another aspect, which is just doing the software engineering of this is being a big problem for us as researchers, because often the essence of the research is to propose a new model with a different structure or different factors in different places. And it can take us more than a month just to code up one of these things. And the nature of research is that you try something and it doesn't work, and then you have to try something else. And it's really slowing our progress how long it takes us to engineer some of these things. So there's been some interest already in the Scala community in supporting machine learning in various ways. There's a very nice package called Scala-La, where the last LA stands for linear algebra, that essentially provides MATLAB-like functionality in Scala. Very nice. This is out of Stanford. OptaML provides data structures for vectors and matrices and does amazing things by automatically producing code for your GPU, not just the CPU, to make things incredibly fast. Spark is a project out of Berkeley that makes it very easy to do handle distributed data, do distributed computation, has shared types for accumulators that make things quite easy. There's another project at Carnegie Mellon. It's C++, not Scala, but you can think of it as an alternative to MapReduce that has updates not for map and reduce, but for update and sync operations on graphs, which is a very nice fit for machine learning. So all of these provide very nice facilities for us to say, take our machine learning problem and distribute it or make it faster by being parallel. But it's not really solving my problem, because it's giving me kind of the same primitives that I did my raw coding in before. It's just making them be fast and distributed. I need something that operates at a higher level, that makes it easy for me to define models and then do inference on them. And a number of people have been concerned with this issue, and there is a rising in the community. It's this notion of probabilistic programming languages. These are languages or DSLs that make it easy to specify a really rich, complicated probabilistic model, and then using the full power of the kinds of things we're used to having in deterministic programming languages. Nice data structures, control mechanisms, abstractions that help us with probabilistic models. And then, once we define the model in a lot of these systems, the inference implementation comes for free as a one-liner. You just, okay, here's the model now, just go do inference. And it was coding up the inference method for some new model structure that was especially tough for us before. So I'm going to do a whirlwind, very fast tour of some other systems, mostly not in Scala, and then talk a bit about the system that we've been building at UMass. Okay, so one system out of Berkeley called BLOG is a generative model of objects and relations. By generative, I mean the graphical model. You visit the variables sort of in some order of some directed graph, generate them one at a time, conditioned on their parents. And it's a nice, small language that lets you specify things with kind of the way that statisticians are used to writing equations. The number of researchers is a random variable that's generated according to some distribution, according to some prior, and then this value will then get used in the generation later, and you build these things up. And it does inference by Markov chain Monte Carlo, which is a sampling method. Church is a system out of MIT that also is a generative model. This lets you tell the generative storyline in scheme, actually. So you write a scheme program with extra random operators that say, that represent the uncertainty in the probabilistic model. And the right mental model is that you can run one of these programs once, and it will generate a single sample from the distribution of all possible values. And you would do inference, say, what's the distribution over A given some particular value on B? Well, you would run this program many, many times, generate many samples, grab just the subset that have the particular value on B, look at the distribution of A in that subset. That would actually be quite inefficient. So the magical, amazing thing that they do is that they do Markov chain Monte Carlo over possible execution paths through these programs. Infer.net is a system from Microsoft that's actually getting deployed in products that builds up a factor graph by a series of declarations. I won't talk too much about that. Let's see here. Figaro is in Scala. It's just been released recently. It's by Avi Pfeffer, who used to be at Harvard and is now at Charles River Associates here in Boston. It's object-oriented. It has this notion of a model, which is a basic building block that encompasses both data and factors, and then they compose together. And Markov logic is a system that lets you define where factors are placed by expressing clauses in first-order logic. And so it's kind of completely declarative. You just say, here's my logical structure, and then it goes off and does inference. So I want to talk a little bit about this declarative versus alternative consideration here. So in a way, in a broad sense, thinking about declarative models has brought great clarity to artificial intelligence research over the last 2 decades. But I've been feeling like it's perhaps gone a bit too far because a lot of the domain knowledge that we machine learning model builders have about what good solutions would look like is actually procedural or imperative. And actually, I'm afraid that I'm using these terms in a much more fuzzy way than you would in this community, which you maybe use them more precisely. All I really mean is not declarative. I just mean thinking about it as a sequence of actions. And I'm actually going to use procedural and imperative interchangeably, which maybe you would hate. I don't really know. But so just read not declarative when I say that. And there's been increasing interest in this direction. Like in our machine learning community, there was a lot of previous interest in combining logic and probability, and there's sort of rising interest in some new systems in combining these non-declarative plus probability systems. And Infer.net and Church are 2 examples. So I'm interested in trying to get the best of both worlds by building imperative tools for creating a declarative model specification. So the approach in the toolkit that we're building preserves the declarative statistical semantics of factor graphs, these lingua franca for building probabilistic models, but provides these imperative hooks for defining their structure, their parameterization, the way that inference is done, and the way parameter estimation is done. So we've been calling these things imperatively defined factor graphs. And the design goals of our system are that, first, it represents factor graphs, that it's very scalable, so it's not just a toy to be used in the classroom, but you can really deploy it at large scale in industry. It's large in terms of input data, output configurations, the number of factors, the total amount of data. That we can leverage object-oriented benefits, that variables, factors, inference methods are all classes that can be subclassed and modified. And that it makes it easy to integrate the sort of declarative and procedural domain knowledge that we have to bake as much smarts as we can into the models that we build. So our system is called FACTORIE. It's a DSL for machine learning with factor graphs, and it's implemented as a library in Scala. Programs in FACTORIE are Scala programs. It's worked out very nicely for us that it's a library and not a new little language of our own creation, because we can now leverage all of Scala's great facility for just doing our data pre-processing and debugging, just printing out diagnostics in the middle of our model definition, and leveraging Scala's very nice type system and OO design capabilities has made it very nice to build subclassable variables and factors and objects here. FACTORIE strives, this is different from some of the previous systems that I described, strives to keep very distinct its notion of variables, random variables in the model, in other words, the data that represent a solution, the factors, in other words, the model or how the model expresses preferences for some solutions over others, the inference methods, and the learning methods. And these are all defined quite separately, allowing a lot of mixing and matching in a way that's worked out very nicely for us. And it is indeed scalable. We run it on billions of random variables with super exponential number of factors, and there's a database back end, so you can run on more data than you can fit in memory. So the way to think about writing a probabilistic model in FACTORIE comes in certain very distinct stages that correspond to this kind of separation I was just talking about. First, you define what you think of as templates for the data, or these are actually just classes to represent random variables. And you can use a lot of data structures that you would use in deterministic programming, which is a bit unusual for people who are used to more basic graphical models. And only one special requirement for doing sampling-based inference is that you provide an undo capability on the setting of these variables. Almost think about them almost like transactions. So you can say, I propose to make this change to my configuration, and then you can undo that. Then you define templates for factors, expressing preferences over certain solutions. And this is, again, distinct from the data representation. So I can here define what my problem is, in essence, and then keep that constant as I hypothesize different possible solutions with different model structures without having to change the stuff upstairs. And then I select an inference method, which often is actually just a one-liner. But you can also bake some domain knowledge into that inference method. And then you read in the data, create variables, and then call your one-liner inference method. All right, so let's get a bit more detailed. So what are some components? And these are actually on the left all class names in the library. So there's a notion of a variable, a random variable, which all have values and can be set and have domains. There are domains, which are some representation of the set of values that a variable can take on. There's a diff object and a diff list, which represents a list of changes to these variables which can be undone. There are factors and the values of the variables that are neighbors to factors and the sufficient statistics of those values. Sometimes factors belong to families that may share common parameters. And some kinds of families are actually templates which are able to generate factors on the fly. And then models are a collection of factors or a way to get a hold of factors. And then some inference method can work on some combination of a model and some data. And here are some examples of kinds of random variables we have, some very standard ones that you'd be used to in statistics, but some other ones that are very powerful but unusual for people in my world, to think about variables that could be set valued or variables that are sequences. So like a couple summers ago, I wrote a machine translation system to go between French and English in this that operated a lot on sequences of words, and actually I wrote the whole thing in just 7 pages of code. OK, so let me show you an example. Let's get even more concrete of a relatively simple model. It'll be this linear chain model that we described at the beginning of the talk. It's going to do segmentation. Here it's actually going to do sentence segmentation. It's going to find the boundaries between sentences. So it's going to put a true at the beginning of a sentence and a false at something that's in the middle or end of a sentence. So first we need some way to represent our data, which are labels and words or tokens. So I'll define some classes for labels, which is a kind of Boolean variable here, and a token, which is a kind of categorical variable. It holds a word in essence. And I should say something about how these things relate to each other. So I can say that they have a trait that says that they're a link in a chain that represents this sequence of words. And this essentially provides those variables with methods for previous and next, so they can navigate up and down the sequence. And these are just regular Scala classes. And so I can also express how the data is related to each other by adding member variables so I can say, well, what's the corresponding token that goes with a label, and vice versa. And this is maybe seems very simple to you, but it's quite a change from the way that a lot of people have been building graphical models in which there wouldn't be these sort of natural pointers between related pieces of data. They might just build up independent arrays and just remember that corresponding indices actually are related to each other. And this has been very nice for us. Also, just the fact that since these are regular objects, we can add arbitrary useful methods to our random variables has been a big win for us that hasn't been in some other toolkits. OK, then we specify our model. So this is a model that's going to have template for factors. So here we're going to say, here's how we say that this kind of factor exists. It's a factor that expresses a prior probability on certain labels independent of any evidence. Here's another one that expresses this factor between tokens and labels. So for every label should have some factor that expresses some compatibility score over itself and its corresponding token, right? Which is what this says. And then here's how we specify this factor here. And then once you specify the model, you just read in the data somehow, create a new inference method, like here's a Gibbs sampler, and then ask the Gibbs sampler to do its work. And it's it's like this one line and this actually having it do its work that just is mind-blowing to we machine learning people, because this is what would have taken a month's worth of effort previously. OK, so this is actually a deep bit of Scala magic that isn't at all what it looks like, actually. Like, this thing is not actually of type label. It's actually some quite complicated, almost like a getter. It's a method that knows how to navigate among sort of across edges of this variable, and I want to of these variables, and I want to try to lift the cover of some of this magic here and show what these things actually create are these things called templates. And I'm realizing that I'm very short on time. I really might not be able to say a lot of this. But we can create templates for these different kinds of factors. And let's then think about what work these templates actually have to do. Right? They're going to have to create factors on the fly when they're needed. So a key operation in, say, a sampling-based kind of inference is that you propose some change to a variable. This proposal method runs. We automatically build up a list of the variables that have changed. And then I need to find the factors that touch the variables that changed. So if I just change the green variables, I need to find the red factors. And I actually don't need the other factors. And so I can be very efficient by I don't have to ask them for scores. I can ask just the red factors for scores. And then I also need to find the other variables that touch the factors that are needed to calculate those scores. And so it's just sort of a complicated process of how to navigate through this data structure. And you think about how to do this. So there's this question of how to find factors from variables and vice versa. And it's Berkeley's system. They built a highly indexed, quite complicated data structure to store this kind of mapping. But it can be quite painful to maintain. And so what we're going to do instead is maintain no such map between these things and solve it in a different way. We're going to say, well, finding the factors from the changed variables is easy, actually, because the number of templates is often quite small. I can just take each changed variable, ask each template, do you care that this variable changed, yes or no? And if it does, give me a factor. And that can be quite efficient. The hard part is, given a factor template and one changed variable, how to find the other variables. And in my experience, when you've got something hard, that's a good place to just declare this to be a primitive operation and then let it be solved in various different ways. So this is what we're going to do. Within a template, you define these methods called unroll, which, given a single changed variable, are responsible for somehow going out to find the other needed variables that are the neighbors of this factor and returning them. So let me show you what this looks like in practice in the code. So here in this template, we could be given a single changed label, and then we just need to find its corresponding token. And well, luckily we have code that makes that very easy. So these things are often one-liners, and correspondingly for these tokens here, we can just navigate through label next and previous to find what we need. Things can get more interesting, say, I won't maybe motivate this, but describe. Here's an additional kind of factor that could be useful. That's expressing the notion that, well, two words that have the same string form, I should have a mild preference that their labels are maybe a bit more likely to be the same. And I would like this factor to express that preference. And, oops, sorry. So, let's see, how am I doing for time? OK. The default kind of parameterization here would look at all possible values of these two neighboring variables, which for this named entity recognition problem would be 5. There would be 25 parameters here. But really, I don't need 25 parameters here, because I only really care that they're the same value. I don't care what the value is. And so the way that we can express this is that actually these templates are an instance of the cake pattern in which there are multiple needed pieces of templates that get pulled together, and we can pull that apart to say that I have a template with two neighbors, but whose sufficient statistics are not the original values of my neighboring variables, but something different that I can define. And I can define methods that make that mapping between labels and values in an interesting way. OK, I planned on going through this in more detail, but let me, for the sake of time, actually accelerate just a bit and show you just very briefly an example of what this looks like running. Let's see here. Ooh, I don't know if I can actually, because I'm not really going to fit this. So here I'm going to train a named entity recognition system on 200,000 words of newswire data, finding names of people, organizations, locations, and miscellaneous named entities. Oops. OK, yep. And so here I just loaded in 200,000 words. Actually, more than that, because I also gathered some test data. I went through and found about 50,000 observable features of these things, of these words. This is running on my little MacBook Air. It runs about 3 times faster on a regular machine. It's just made its first pass of training through all these things. It's already getting about 97% accuracy. And on its third iteration, it's done. It's got 98% accuracy, and here are some examples. So it's found that EU is an organization, and that Britain is a location, and so on. And this kind of training in an earlier system that we did took about 6 hours, and we just finished it in 20 minutes. And it's, Scala didn't slow us down. What FACTORIE did was it let us use some fancier new machine learning methods that were quite a bit more difficult in previous systems. OK, let's see here. So I have about 3 minutes left, and so I'm going to skip a number of things, including some stuff on topic modeling. A minor point that I want to make here just extremely briefly is that we've also been very interested in large-scale distributed parallelism, and we have found some great advantages to thinking about how to do parallelism and thinking about how to do the machine learning inference at the same time in an intertwined way that actually makes things significantly faster. So it's like the inference method is thinking not only about how to solve the problem, but thinking about how to most efficiently distribute the data across the machine. And this is one of the ways that we're very excited about, say, integrating ideas from FACTORIE, which knows about the machine learning modeling, and with some of these previous Scala machine learning aids that I described earlier that are thinking deeply about distribution and putting them together in a deeply intertwined way. I don't have time to show this, but this is with parallelism without being smart about using machine learning to think about parallelism, and when you do them together, they can make a very big difference. OK, so I'll just conclude with just a couple of points here. So what we love about Scala, I think, is not going to be any surprise. It's just the same things that you love. We've made extensive use of traits, and it's been a big win for us. We also use implicit parameters, say, to keep automatically pass in diff list arguments. We've made a lot of use of function arguments, say, to capture closures for partially built factors that still need more information to finally create them, and you get that information later. We've used implicit conversions and the cake pattern in a number of places. But I guess what I am more interested to talk about are some things that we'd still like to see from Scala. And I have 3 things to say. So one is, it would be nice to have just a little bit more efficiency. And I know that there's a desire not to do premature optimization, but I kind of feel like we're at the point where just a little bit more optimization wouldn't be premature. So there's some places where we're scared to use the Scala collection library just because we just get surprised by some strange inefficiency there. We're tremendously happy that it seems that this for loops over integers seems to be fixed. It's no longer wrapping integers and creating a lot of objects for us. This mattered to us a lot. It was quite painful to just do while loops everywhere. But we still get surprises. Like just last week, we were using signum, which is one of the it's a single operation on the CPU. It just gives you the sign of the number. But this is what it turns into in Scala, unfortunately. It boxes. And it's just mind-blowing to us. It's just so sad. So it's some of that. And point number 2 is I've desired for a long time constructor arguments for traits. Right, this would let me get manifests for the type arguments of traits, as well as a bunch of other things. And I know there's been discussion about this for years. And Donna Malari, who I think has been working with EPFL folks, I think has a way to do this. And I know it's been sort of in discussion, but not happened yet. And lastly, this is my last thing, and then I know I'm just a little bit over time, but so this is something that I've wanted so often, and I don't know whether it's considered or being discussed or whether it even makes sense, and I thought this audience could tell me. And this is the following issue. So, when you can stack some traits that override a method, and when you call superfoo here, as you all know, I'm sure, there's linearization, and the meaning of that superfoo depends on the linearization of the traits it will cause, sort of the implementation of foo, the next step through the set of traits. I would like the same kind of thing to be possible when I say extends superfoo in an inner class. Right? So right now, if I say I have an inner class foo here, and then I have some traits that create new inner classes that extend superfoo, this superfoo is just statically refers to this outer one. And I would like to be able to stack a bunch of traits here and have foo here incorporate all of the aspects of all of the subdefinitions of foo and all of these traits here. It's like a kind of cake pattern that lets me reach into an already defined inner object and add some functionality to that pre-existing inner object. With that, I'm sorry I'm a little bit over, but I'll close now and I'm happy to take questions. Thank you.